Okay, so the first idea here is there are exceptions to the octet rule. This is a notable one that you just kind of have memorized. So boron trifluoride, so BF3, boron can actually have an octet be filled with only 3 bonds. So here it only has 6 electrons, and that's okay. And so like this is a trigonal planar shape. We'll go into that on Tuesday, but this is just a really notable exception. And then, so boron is cool with only 3 bonds. So just have that in mind, okay? And then some of them, most of them that, you know, are exceptions to the octet rule, they actually have expanded octets. And so if you look up at the periodic table and look at the 3rd period, sodium all the way through argon, that 3rd energy level down can have expanded octets. And so what ends up happening, like phosphorus and sulfur are kind of the 2 most notable ones for doing this. What they'll do is they'll fill their 3s and 3p orbitals. The 3d orbitals, the d block in the 4th period, so scandium through zinc, if you're thinking about where that is on the periodic table, they will actually, instead of just having 8 electrons, 8 valence electrons, they will have, they can have 10 or even 12. And those extra electrons are going into that 3D sublevel. So that's the thing. So let me show you what that kind of looks like. Before I move on though, on the AP exam, what they'll want you to understand is, they'll say, why can nitrogen not have an expanded octet, but then phosphorus can? So nitrogen cannot, because in the 2nd energy level, there are no d orbitals. Like D doesn't start till 3. See what I mean? So that they will ask you about that. So here's an example of the expanded octet. Here you can see that the phosphorus has 2, 4, 6, 8, 10 electrons instead of just 8. And so this PCl5, what's actually happened here is if we look at the electron configuration of phosphorus, it needs 3 more electrons to fill its octet. So you would want it to end in 3s2, 3p6, and then it would be a stable electron configuration of a noble gas. How do you feel about that? But what ends up happening is here it actually has 2 more electrons past this 3p6, and they are in the 3d. Okay, so it would be like 3d2. Isn't that crazy? Who knew, right? I did, but I'm just kidding. And it has an explanation here. The 3D and the 3P sublevels are really close in energy, and so you saw the weird shapes of those d orbitals. They really are intertwining and in the same area as a lot of those p orbitals, right? And so that's the thing. They're just really close in energy level. And then this is the same problem you run into with your transition metals. They'll lose their s electrons before they lose their d electrons, and vice versa. And that's because they're also overlapping. So here's sulfur tetrafluoride. This is a common one that you see here. And notice that sulfur here is actually showing 12 electrons. So because it has these three bonds here, and 3 make 6. And so those again are filling up, for sulfur, they're filling up 3d orbitals. Good times. And so xenon, even if you look where xenon is on the periodic table, I've seen questions, similar questions to like, xenon can form xenon tetrafluoride, but you know, neon cannot bond in such a manner. Like, why is that? And again, you would go back to neon is only in the 2nd energy principal energy level, but xenon can have expanded octets because the 5th energy level contains d orbitals, right? So 5p and 5d are similar energies, and so that's why they can fill. This looks really complicated. It's scary to draw if you're asked to draw these, but it's not hard. So you draw these the same way. So let me show you. And so we have xenon and then F4. You know, your noble gases don't actually have electronegativity values because they don't bond, but you know, slow. And 0 really, I guess technically. But that's going to be my central atom. And then so this has 8 electrons, and then we have 7 times 4, so that's 28. And so on my picture, my Lewis structure, when I'm done, I should have 36 electrons showing. So you go through the steps like you do on all these. They're actually a little bit easier because generally you'll have that like central atom, and then there'll be 6 Fs or 6 Cls or something. So it's not, it's not hard to kind of figure out what to do with them. But anyway, go through the steps, draw a single bond between your central atom and your terminal atoms. No big deal. And then you're going to go back behind that, and you're going to fulfill the octet for your terminal atoms. And so in this picture here, I have 32 electrons showing. I'm supposed to have 36 in my diagram. So any extras, remember, got to put on your central atom. And so I did. And that's the picture. So it's not any harder. It's just, you got to be okay with the fact that when you go to check this, because it's in the 3rd energy level or greater, xenon is okay to have more than those 4 bonds, or your 8 electrons overall. So as far as knowing which one's the central one, it's generally the first one listed in the compound, and then it's the least electronegative. That, which one goes in the middle, that doesn't correlate to necessarily the energy level. But yeah, and just be careful with the way you're saying that, because like the electron configuration of phosphorus, sulfur, chlorine, and argon, they don't actually have a D in their electron configuration, because that's in the next period. So 3rd energy level or higher. But yeah, I gotcha. That's not wrong to think like that. Okay, so there's your expanded octets. So formal charge. Formal charge is really complicated, but so here, formal charge is just basically a way of assigning a charge to each atom in a compound. And so when you do that, and you add them all up, for something like water or methane, where it's a neutral compound, the charges have to add up to 0, because the charge on the compound is 0. Something like sulfate, SO4 2-, the charges on all the individual atoms have to add up to 2-. That's all it is. And so here's a formula. Wait. No, I'm just kidding. Just here, I'm going to tell you how to do this, okay? So just ignore this. And this is how to do formal charge. Formal charge is equal to valence electrons, which you can find on the periodic table, minus sticks plus berries. Okay? Valence electrons minus sticks plus berries. It's good. It's good. It works. Or you can do that. Is a stick one thing or 2 things? Is a stick one? If it's a stick, is that one thing or? This is one, yeah. And so, right, so you count it as one thing. I see what you're saying, but count the sticks and berries. Just forget about, what you're doing for a second. All right, so let me show you how this goes down, okay? The main idea is each atom in a compound should have a formal charge closest to 0, right? And so when we assign these formal charges, let me take you through this. Chlorine has 7 valence electrons. And now I'm going to count the sticks and berries. 1, 2, 3, 4, 5, 6, 7. So the formal charge on this chlorine is 0. Nitrogen, it has 5 valence electrons. 1, 2, 3, 4, 5. Its formal charge is 0. This chlorine and this chlorine are also 0 for the same math. It's the same thing. So cool, the formal charge on all these are 0, and that this is a compound, it's neutral, so it should be 0. So on this chlorine, again 7, and then I have 7, so it's 0. This chlorine is also 0 for the same reason. And then nitrogen has 5 valence electrons, 1, 2, 3, 4, 5, 6, 7, and that equals -2. This chlorine is 7 minus 1, 2, 3, 4, 5, that equals +2. Well, the formal charges in this add up to 0. So, but this chlorine and this nitrogen, they had formal charges that were -2 and +2. So, of these 2 choices, this one is better. How do you feel about that? Well, sometimes even in the best Lewis structure possible, you might have something that's a +1 and a -1. But like in the less desirable example, you might have a +2 and a -2. So yeah, if you take the absolute value of all the formal charges and add them up, the one with the smallest number is the best one. But I haven't had a situation in these kind of cases where I've actually had to do, like, it's pretty obvious when you go to check it, you know. So anyway, moving on, I'm going to let you guys try this a little bit. So here's all their work where they were trying pretty hard how to do the things. Okay, so take on your whiteboards, and these depict the polyatomic ion thiocyanate. I don't know if you're familiar with that, but this is it. And so in this case, sulfur and carbon have the same electronegativity, so it's hard to tell which one goes in the middle. And so assign the formal charges and then pick which of the Lewis structures is the best one. As y'all are working that out, I'm going to just kind of quietly put my answers up here. So you can compare as you're finishing up. No, these are already drawn. So what the deal is with this is when you add up all your formal charges, what should they equal? Yeah, so it should equal 1 minus -1. Nitrogen is more electronegative. Nitrogen, oxygen, and thorium is less electronegative. And that's the thing. When we get to next unit, we'll all don't do this. This unit, the next one is the most abstract. After that, the math instead. Like the person that makes the highest grade on this test will be like vastly different on the kid in the next test. That's what happened last year. And then like my math people, like I had one kid that made highest grade on like almost every test except these. Like he wasn't feeling his math. And then all the other kids did. And so it's like I had oddball kids on these two things. That's good. I was ready for that. All right, so how did you guys fare? Left or right? Which one's the correct one? Right. Okay. So if I see the formal charges are 0, 0, and -1, then yeah, this one is better. And then your formal charges, if you count up your valence electrons and you do the Lewis structure like I showed you, your formal charges will all add up to what they're supposed to be if you follow the directions. But this one has overall larger number of formal charges. So there are 3 ways to check yourself before you turn in a paper with the Lewis structure on it. Count up your valence electrons, make sure it's the right number. Okay. Then also make sure everything has a full octet, and then also check your formal charges. They should add up to the correct charge. So what's going to generally happen with these? Somebody was asking me last period, on the AP exam, like, I don't know, I think they were concerned about like what kind of question this would be like. And so on the AP exam, when you're having to draw Lewis structures, if they ask you to draw something which had a couple carbons and an oxygen and a hydrogen, like on the test with no lines or anything, they'll throw out for you like the order and where they're supposed to be. So you'll know that, like, you know what I'm saying? Like, you'll know where you won't need to know like crazy organic molecules and their shape and stuff. They'll put out kind of a skeleton for you without connecting the lines, but then you'll know in relation, like, this Freeman, I don't know if I can figure out where to put this one beside this one. You don't have to worry about that, but you need to worry about formal charge and like the correctness of it. So if you can do what I'm teaching you, you will be fine. All right, moving on. So they're doing the math. Math is fun. Okay, so here is draw the Lewis structure for sulfate and then check it using formal charges. So draw sulfate and then check it using formal charges. If you skipped this step, don't. Thank you. That doesn't add up. Yay. How do I feel about this? Okay, no biggie, right? Math. Okay. I see a couple people looking, so I'll keep it up there for them. Victoria, you got a question? So there's 4 oxygens, right? Each one's -1, and then you have to add up the 2 from the sulfur, and then 4. Subtract. Now, it's worth going, if you understand that, you're fine, but it is worth mentioning something real quick. This is, I haven't seen any questions on that in AP exams or release exams following this line of logic. But if you draw it like we just drew it, which is fine, you'll get your formal charges, and you'll see that, you have a formal charge on each oxygen, and then your sulfur has a formal charge. But then, because sulfur can expand its octet, like the best drawing for sulfur or sulfate looks like this, because now there's only 2 atoms that have a formal charge. Like, don't stress about this. Look, don't worry about doing this on your own. But if you were taking the AP exam and they gave you both pictures, could you pick the one with the best? Yeah, even though this looks weird, it's right. So this is the right sulfate, but don't worry about that, except for the formal charge reasoning. All right, so this is something that you should feel kind of comfortable with. This is what the POPL was concerning. High potential energy, and so if we think about high and low potential energy, what we got to think about is that graph. So there's 0. High potential energy is above 0 or close to 0. Like, this is the lowest potential energy. Right here where they're far apart, remember that was where, it started coming back up to the axis, the x-axis, closer to 0, right? These were close together, these were bonded, and this is where we pulled them apart. So this says, when I say high potential energy, I mean that I'm not negative, right? Closer to 0. Low potential energy, the lowest potential energy is here. This is where the bond is formed. That's where you're maximizing the Coulombic attraction of this nucleus's protons and the electrons of the other atom, and vice versa. That's it. Are you feeling okay? Can you imagine if we had had this conversation like 3 days ago? I would not have probably went well, or 5 days ago. So you're learning things. Now, if you haven't already learned this for the 15th time, this is important. Like, I hope that you remember how last test you had to look at the bond energies, and you didn't have to draw it, but you had to know that the energy is released. So it's negative, it's exothermic for making a bond, and then endothermic for breaking a bond, and then you put them together. Well, now guess what, homies? You're gonna know how to draw the Lewis structure. So you got to draw the Lewis structure and do the same thing. Good times. So don't forget that we had talked about the enthalpies already. And remember the energy needed, like if I make a bond here between these 2 magnets, the energy needed released, that's so cool, I mean you can just feel it, is the same as the energy needed to pull it apart. Okay, and it just has opposite signs for that enthalpy. Whoop. Potential energy has been decreased. Come to rest at the, no, I'm just kidding. So there's your enthalpies. Notice that breaking a bond, positive enthalpy, making a bond, negative enthalpy, same magnitude, different signs. You should feel familiar with this diagram. This is a thing. And what they'll do in the AP exam is they will draw on top of each other. They will draw, like this is a single bond, right? And then they'll draw the double bond and triple bond on top of that. But what I told you guys, and I really wish this was up here for actually putting energy into it to get it, because when you put them too close, you do have to put energy into positive energy to overcome the repulsion. That's where the bond is made, and this is as we separate them, they really cease to, on our measurable scale here, to be attracted to one another. It never reaches 0, even if you're across the universe. But so bond energy and bond length, okay? As far as the size of the atom that is actually in the bond, the bigger the atom, right, the lower the Coulombic attraction, because farther apart. Remember distance. If I have magnets farther apart, they're not going to be as attracted to each other. So closer proximity means you have a stronger force of attraction. And so if I draw this out, like if I make my carbon here, there's carbon, 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 and then I draw chlorine, bromine, and iodine, right? After I go down a group, they get larger. So this is the chlorine, not to scale, but and there's the bromine, And there's the iodine. Yay! Right? You got to think about that distance that we had talked about between the nucleus here and the electrons, and the nucleus here and the electrons, the nucleus here and the electrons, and the nucleus here and the electrons, and here, so forth. So if I look at this distance, obviously the distance is getting larger, and then if I see that, I can see that the bond energy decreases because this is the energy needed to break that bond. This is positive energy to break that bond. These are going to be easier to separate because the Coulomb contraction is less. And then you can see the distance, that's the distance, is greater. Those are inversely related. Isn't that fun? They would make a coding on the calculus graph. Yay! Moving on. Alright, so answer this question for me on your whiteboard or on your paper, and I'll call on you as necessary. Be careful with this wording. It'd be the same, wouldn't it? You have to look at the wording of it. Because it says lowest potential energy, then that's the potential energy graph. Lowest bond energy is enthalpy. Think bond enthalpy, the energy needed to break the bond. Like, so you have to know what word it's talking about. Fun times. Y'all look so sad. A, which molecule has the least amount of potential energy associated with this bond? So y'all can see how this graph, that graph with that's never going away. And so I'm going to keep referring back to it. It's a thing. It's on your test. Isn't that gonna be fun? Like, you're super going to get that one right. Hopefully. Oh, I'm sure it's like I remember it's like number 11 or something. Yes. So on your test, like, it has 3 different bonds and no, I don't know. And I always go back and edit them anyway. So which molecule has the least amount of potential energy, Sarah? Just pick one and just let's talk through it. The first one. And so what made you kind of think about that? All right, so the least amount of potential energy, this is what we're talking about here. We're talking about this graph again, right? I was heading the right direction, and then I got off course. That makes me feel a little bit better. So this is distance, right? So when you're reading these graphs, this is distance, and that's potential energy. And so the shorter the distance, the least amount of potential energy. So you're right that one is correct, but can you come back behind her and explain why, Kat? What? Oh, no, there's somebody in the hall. Right, and so, yeah, these are, and you have to think, the greater the attractive force is, the lower the potential energy, right? Because once they come together, right, that's the lowest energy state. When I say low, I mean dip it down in the graph. So yes, one is correct, and for that reason. And so on 2, which bond has the lowest bond energy? So what did you get on that one, Courtney? Yeah. Right, and so if I were to try to rip these apart, right, I would have to overcome this potential energy here, right? And so that red line is number 2, and so the bond enthalpy would be less. And you have to think about it. It is less because it's the opposite sign to break it, and this is negative. It all works out, but it's just like, huh? Well, it's not even lower magnitude. When you break a bond, you flip the sign. So it is lower magnitude, but the process that we're talking about is a positive enthalpy. So we don't have to, we're not having to fudge the system and put absolute value brackets on it. It is correct in the way I said it, and you don't have to, you have to keep going back to that breaking a bond positive thing, and I'm going to keep going back to it too. Yes, sir. You have a question? Is positive potential energy is up in here. We're having to, and that one shouldn't have come up above the axis. I'm sorry. The positive energy on this one, that is where the atoms are so close together that I'm having to put energy into forcing them together because of the repulsion of their like charges in the nuclei.
So you use positive potential energy to show
positive energy in general. Nope. Because negative, this attractive force, I actually, when things are attracted, they come together, they release energy. I don't have to put energy into it. This is the release of energy because it's negative. Remember, like exothermic reactions, negative enthalpy. Isn't this fun? Super abstract. But at least we have graphs and magnets and time. Oh, wait, you don't have any time. But, alright, moving on. So, lowest potential energy has the shortest bond length, lowest bond energy, longest bond length. Alright, so now we're going to move on from the idea of just it has to do with atomic radii to actually bond order. Alright, so bond order, single bond has bond order of 1, and so you have to think about this proton, or how many protons ever are in here, being attracted to these electrons and vice versa. And so if I increase the number of electrons, I'm increasing the coulombic attraction because the magnitude of the charges is greater. And so it draws those nuclei closer and then still with a triple bond. Somebody always asks me, is there a quadruple bond? No, because you would start to have this repulsion happen in between the nuclei. They would be drawn too close. There's a line there. So anyway, it was National Chemistry Week. How appropriate. But that's what we're talking about. When we draw these lines, that's what's actually happening there. So notice the bond length is decreasing. Can y'all see that? The bond length is decreasing. And the bond energy, the energy needed, if you think about these being magnets, I'm holding two magnets, I'm holding two magnets, I'm holding two magnets, which are going to be the hardest to rip apart? The closer ones, because the coulombic attraction is great. Alright, so I think I just went the wrong way. It is what it is. So let's take a look at this. You can still see the bond order is 1, 2, 3. And then the bond energy goes up. I mean, a lot. Goes up a lot as you increase the bond order, and the length goes down. So again, these are inversely related. How are you feeling? And so this is in case you didn't get it, let's make this black, and we'll make this one red, and this one blue. Let me give myself an axis to work with here. Again, this is like the most important thing so far. The fluorine's graph with the single bond, the length would be the longest, right? So this is length down here. So if I draw fluorine in and the energy isn't that big, like I didn't give myself a lot of room to work with, but we'll do the best we can. And then oxygen would have a shorter length than that, and it would be a little lower. And when you take the test, they're pretty close together. You have to really look at it, to be honest with you. And then the nitrogen, the triple bond, would have the lowest potential energy. Like that. And you look at a graph and figure that out now. Okay. That same kind of graph would also work for if I had 3 different radii. The carbon connected to the iodine, bromine, and all that fluorine. So this same graph would work for that, where the blue one would be like my carbon and fluorine, carbon and chlorine, and carbon and bromine. Do you see? Because the distance gets bigger. So it makes a graph like that. But it's the same stuff. again, 1, 2, 3, single, double, triple. When bond order increases, the length decreases, the potential energy decreases, so you're down deeper in that trough there, and the bond energy increases. And when I say bond energy, think bond enthalpy, which is the energy needed to break the bond. How are you feeling? Still okay? Okay, so let's give these two questions a try, you guys, on your paper. This bond stick model, so this is a triple bond, and that's a double bond, basically. What? Oh.
I'm used to the straight lines.
Yeah, well, that's okay. I helped you. Excuse me. Yes.
So with resonance structures, how it's like actually like the actual ozone molecule would be like the average of the two
Yes.
ones. So how can that work unless they like have like the like the local how do you have like an average like 1.5 like that work? Unless they're like moving between like elements.
Right. So I think what you're talking about will be answered when we get to the sigma and pi bonds in the, see your little benzene ring you wore? I still forgot to take care of this picture. But those, the hybridization of the orbitals kind of tell you how they do move around inside of there. But as far as some of them are delocalized like you're talking about. And that goes in when you're reading, or I guess you already did your homework. But when we get into the what is it called? I just said the word a second ago.
You said
Yeah, the hybridized orbitals. Right. And so they do overlap. All right, let's take a look at this. Again, on number 2A, the carbon-carbon bond, which molecule has the lowest potential energy? Yes, the first picture, and why is that? Yeah, so you have the higher bond order, so they're closer together, which would decrease the potential energy. You know, can you see how like when this is on test, because this is all like this is your test, like this kind of craziness where you're like, can you already feel like in your head how you're gonna have to just really know your stuff? Okay. No pressure. The carbon-carbon bond, which molecule has the lowest bond energy? Cat. Yeah, and so why? Yeah, and so since it has a lower bond order, the distance between the two nuclei are less, so there's less greater. So there is less Coulombic attraction, and they would be easier to pull from apart from each other. Isn't this fun? Yes, sir.
So we're just like not count the hydrogen bond, or
So they would ask you, oh, as far as determining that kind of stuff. No, that doesn't matter. They're gonna. Yeah, they will. You'll know what part of the molecule they're referring to. Yeah. So good question. These, going back to Jonathan's question, he asked a good question. Y'all know how there was a chart and it said a CH bond had so many kilojoules per mole for the bond energy? That's the same for this CH bond as this CH bond. So, and then this triple bond in this molecule is the same as triple bond in another molecule between two carbons. That's what you get. That chart works for everything. Okay. Space, that doesn't matter. Resonance structures. Here's the deal, you guys. For resonance resonance structures. If you draw nitrate, which I'm going to draw nitrate for you, nitrate has one double bond and 2 single bonds. You can just take my word for it. You want me to go through the steps? Who said yes? You sillies. So there's nitrate. Okay? And so everybody's octet is fulfilled and it has the right number of valence electrons and everything's fine. But when you draw nitrate, is it not equally legitimate to put the double bond here? Or could you also put the double bond here? Yeah. And would that change the formal charge of anything? No, it'd be the same. So there's what's called resonance structures, where what's really happening is all 3 of those are really going on at the same time. And let me show you what that, and so that's called the resonance structure. So there's three equally valid Lewis structures for this. And so on ozone, y'all drew ozone yesterday. And so ozone has a double bond and a single bond. And so, but it's also equally valid to draw the single bond here and the double bond here. And so when we go to find the bond order in this ozone molecule, its bond order is not 2 and it's not 1. It's actually 1.5. I mean, if I ask you if you could draw them both ways, it's not so single, it's not double, it's somewhere in the middle, would you not tell me, well, I guess it's 1.5? Like, just intuitively. So to do the math for that, you just have to say, well, 2 plus 1 divided by 2 gives you 1.5. So a double bond and a single bond, or a second bond order and a first bond order, and there's 2 bonds. Is that the worst thing that's ever happened to you? No. Okay, so moving on. With that nitrate, when you are asked to draw the Lewis structure for nitrate, something that is clear that there's a resonance structure and there's actually 3 resonance structures, like you have to draw all 3 and you have to put these arrows in between. I haven't seen on an AP exam where they ask you to draw all 3, but there's multiple choice kinds of questions, okay? It could happen, you never know. So let's look at the bond order for this nitrogen. I have a 2, a bond order of 2 and 1 and 1, and then there's 3 bonds around nitrogen. So the bond order on that nitrogen is actually 1.33. So in this case, if they were asking about the bond order on the oxygens, again, there's 2 oxygens. There's 2 bonds between the carbon and oxygen. This one's 2 and this one's 1. So it'd just be 2 plus 1 divided by 2, which is 1.5. Same that we just did a second ago. Okay. So this, I wish you the best. It's not hard as far as what we just did, but I bet you'll get the answer wrong. And please, someone surprise me. Okay. So think about what you're doing. Look at your yeah. You got this. Go ahead. You have to do the bond energy here. How many resonance structures are for this first one? 2. And how many for this one? Right? Do you see what I'm saying? Like, you have to think of, it's not pictured, but it's there. Y'all know the bond energy in the first one is 1.5, right? Can you see it? All right, figure out for the next one. I guess I already did it, didn't I? Bond order, I'm sorry.
I was like, where on that?
Bond order.
You said it like 3 times, and I was like,
None of these sound anything the same. I'm so sorry.
every time you said it, I got more nervous.
The bond order, I'm sorry, which is related to the bond energy, but inverse. Which structure has the shortest bonds? In my defense, the reason I was thinking it was because of this question.
Wait, bond order and
Right.
said that
Bond order.
higher.
Okay.
It's okay. You probably decided.
Right.
I'm not.
Potential energy.
It gets kind of like it all.
It's all straight in here. I'm sorry. I'm gonna stop talking now. We're almost done, thank God. Explaining this all the way through twice is quite difficult. Okay, so let's see. You should have figured out that this was the bond order for each nitrogen, yeah? Any problems with that? So, Grace, which structure has the shortest bonds? You don't, there's nothing in a picture or anything other than your brain that will help you answer this. So that's the bond order for that one, and that's the bond order for that one. So which one? I'm sorry? The first one has, and you're right. Did y'all think the second one had the shorter bonds? Yeah. What? If you thought that. Okay, and so let me explain it to you. Okay, let's just think of numbers. This one's smaller and this one's bigger. If I had told you that the bond order for this one was 1 and the bond order for this one was 3, would you have had any trouble telling me which one was a shorter bond? It would have been the first one, wouldn't it? And you wouldn't have had any trouble. This one has a higher bond order than that one. So as the bond order increases, the length decreases. And that's why I said everything all crazy a minute ago. But do you get it? Isn't this like, can you already see how you're going to miss this on the test? And then I'm going to give you the test back, and then you're going to be sad. But can you already see it? I'm sorry. But I'm trying to get you ready. Right? Better to talk about it now. I'm not gonna lie, that confused the heck out of me last year. I was like, what? And then I didn't have anybody ask. So there you go. And so this one has the shorter bonds. Yay. And that's it. So we're done with this PowerPoint. Yay.